Okay, we'll go ahead and get started. I did not have a chance to grade your homeworks. I did not have a chance to grade your homeworks. I will get it done. Here we go. I will be sure to get it done next week. Oh, let's see. Okay. So hopefully we're good. So anyway, I did not have a chance to grade your homeworks. I will have it done by next week. Things just got too busy for me. You see, I have handed out your homework number to do 2 weeks from today. And the first couple of problems are dealing with the R curves and the R ratio that we talked about last week. And then problems 3 through 6 will be on the stress intensity. Well, the first 3 problems will be on the R ratio stuff that we talked about. And then the second 3 problems we'll be covering today, it'll be the material related to the stress intensity, related to the stress intensity factor. And for those of you listening to recordings or online, the homework will be posted tonight. Plus, also by next week, I should be able to tell you my tentative date for the midterm. It will be either, just it will likely either be on it will likely either be on the 24th or the 31st of October. So either 3 weeks from today or 4 weeks from today. And in any case, it'll just be the material on the first 2 homeworks, which is covered on the midterm, because I never give test questions on material that hasn't been that you haven't done homework on. And again, by next week, because basically teaching 2 classes, it'll basically be one of my classes, the midterm will be the week of the 23rd. The other class, it'll be the week on the 30th. And I'm just going back and forth and deciding which one will be which week. So as I said, just in terms of tentative planning, figure the 24th, 4th, or the 31st will be your midterm. So start checking your calendars, and next week we'll talk and we'll set the date for the midterm, because as I said, if there's something where people have business travel or whatever, we will work around it. So I think that's it as far as and the midterm will be, and one thing I will tell you right now, the midterm will be during the class period. And even though the class period is 2.5 hours, it won't be a 2.5 hour midterm. I mean, the two things is, first of all, the midterm will only be like an hour and a half, hour and 15, hour and a half, something like that. And also the thing you don't have to worry about is that will be all for that week. It won't be like, I won't make you sit through an hour lecture and then have to worry about taking a midterm. That's just like not fair. So anyway, so any questions on administrative type of stuff? And as I said, I will have your homeworks graded by next week. And actually looking, so yeah, so I'll confirm next week, but probably heck of a way to celebrate Halloween, but to ensure that or no, it'll be either the 24th or the 31st. I'll decide next week. And even if it is the 24th, even though you won't be turning in your homework until the 17th, you will have the solutions, and I will have your homework 2 graded by the time of the exam. So, so you'll have your graded homeworks with you for the exam. So, any questions on administrative stuff? Hey, that will get to work. Just make sure that my pen's cooperating. Okay. Okay. So last week we talked about the R curve and we talked about the conditions that lead to stable or unstable crack growth. But what we'll be doing today is talking about stress analysis of cracks. So that's where it is. Okay. So anyway, for crack configuration subject to external forces, it's possible to derive closed form expressions for the stresses in the body. We're like pretty much everything this semester in this class, we're going to assume isotropic linear elastic material behavior. So what we're going to do is it's going to be we're going to do most of our stuff in the Cartesian system, but we'll just deal a little bit with the polar coordinate system. So we talk about a polar coordinate axis where we have the origin at the crack tip, and we define any point around the crack. It's at some angle theta from the horizontal, and it's from some distance r from the tip of the crack. And what we're talking about, so for some point in our structure, angle theta, distance r, we can define our stress state. And obviously, depending on how we apply the loads, we can have a fully populated stress tensor with normal stresses in both directions and in plane shear stresses. So given this coordinate system, we can show that the stress field in any linear elastic crack body, and the derivation of this is beyond the scope of our discussions here. So we can say that our stress is equal to some constant k divided by the square root of this radius times some function of this angle theta, and we're going to be defining all this. And there's a very complicated summation term where we sum from m equals 0 to infinity of a constant am times the radius to the m over 2 power times some function g related to the mode m, which is a function of theta. So here's our baseline. So here's our baseline equation. K is a constant. Fij is a dimensionless function of theta. And for these higher order terms here, am is the amplitude, and this gij is a dimensionless function of the angle theta. Now, the higher order terms, so all of this stuff here depends on the geometry. And we'll be having lots of specific expressions for this stuff depending on various and sundry specimen and crack geometries. But the solution for any configuration contains as you see here, the solution for any configuration. So no matter what our specimen geometry, what our crack geometry, we always have this square root over 1 over the square root of r term. In just a second, I forgot to put my phone on silent. So there we go. Here we go. So this displacement varies with 1 over square root of r. And what's important here is because we're dividing by the radius, is that if you look right at the tip of the crack, R is equal to 0. And when R equals 0, you remember from elementary division that when you divide anything by 0, it's a singularity. It goes to infinity. So it does describe a stress singularity. So the stress goes to infinity right at the crack tip, and the stress goes, and we'll show some plots on this later. The stress goes asymptotic at R equals 0. And the basis of this relationship, and in one of the appendices in the back of the textbook, they actually go through a detailed discussion of it, but it's beyond the scope of our discussions here. And this isn't the first time we've seen this idea. In our early discussions, we talked about the Inglis analysis also predicted a stress singularity at the tip of a perfectly sharp crack. And so, yeah, so we talked about all this. And yeah. So there's 3 types of loading a crack can experience. And you see this terminology a lot when people talk about fracture. So the 3 types of modes are mode 1, mode 2, and mode 3. So in mode 1, what you have is the load is applied normal to the crack plane, and it just straight up opens the crack, and it's the simplest type of loading. You pull on the crack, you open the crack, you grow the crack. Then, but this is a normal mode. Then mode 2 is an in-plane shear mode. And what it does is it slides, as you can see in this cartoon here, it slides one face of the crack with respect to the other. And then mode 3 is out of plane shear. So you're still sliding the faces, but it's outside of the main plane of the crack. Now, the key is a lot of times when we talk in our discussions, both analytically and when we talk a little bit about the type of testing that can be done, usually things tend to be developed in terms of mode 1 or mode 2 or mode 3. But in reality, a crack body can be loaded in any of these modes individually, or if you have a body under a multi-axial stress state, it can be loaded in a combination of 2 or 3 modes. And we'll talk about how to handle the case when you have a combination of modes. And the nice thing is, preview of coming attractions is that because, particularly for right now, because we're looking at a linear problem, we can use the simple idea of superposition, where you can take the response for mode 1, add it to the response of mode 2, add it to the response of mode 3 if necessary, and you can get the corresponding combined response. So the same way we talked about the strain energy release rate as one of the key types of parameters in fracture analysis. And by the way, next week we'll talk about how you can relate the strain energy release rate to what we're going to talk about now, the stress intensity factor. But in terms of stress analysis, the stress intensity factor is the key idea. And each mode of loading produces the 1 over square root of the radius singularity at the crack tip, but the proportionality constant and this function we talked about depend on the mode. And the key thing we're going to do is we're going to replace that K that we talked about with the stress intensity factor, where the big thing is it's the stress intensity factor is you just take that K constant and multiply it by the square root of 2 pi. And the stress intensity factor is usually given as a subscript to denote the mode of loading. So it's I didn't do it for the PowerPoint, but it's K sub 1, K sub 2, or K sub 3. And then you can write, and we're going to come up with some specific expressions, but just in the general case, the stress fields ahead of a crack tip in an isotropic linear elastic material can be written for modes 1, 2, or modes 1, 2, or 3. So for mode 1, we have that the limit as the radius goes to 0 of the stress under mode 1 loading is equal to the mode 1 stress intensity factor divided by 2 times pi times the radius times the function associated with mode 1. And again, we're going to define all of this, and this is a function of the angle theta, which we're going to give lots of examples momentarily of how we can define these functions. And then for mode 2, we have the limit as the radius goes to 0 of the stress for mode 2 is equal to K sub 2 divided by the square root of 2 times pi times the radius times our function of theta appropriate for mode 2. And then finally, just to make the point, for mode 3, we have the limit as the radius goes to 0 of the stress associated with mode 3 loading is equal to the mode 3 stress intensity factor divided by 2 times pi times the radius times our function of theta appropriate for mode 3. And we say the limit because as we'll show shortly, all of these things we're talking about the stresses around a crack, they're only valid in the region right around the crack. We'll emphasize this again, but when you get, at some distance away from the crack loses its influence, and you just have the far field stress that you apply to the structure. Yeah. No. Next week, we're going to get to the magic point where we're actually going to start allowing for plasticity at the crack tip. But for right now, this moment, we're assuming everything is linear elastic. So for a mixed mode problem where more than one loading mode is present, the individual contributions to a given stress components we talked about, we can add them together. So the total stress is equal to the stress from mode 1 plus the stress from mode 2 plus the stress resulting from mode 3. Here we go. And as I said, it's due to the idea of linear superposition. So this way, if you have a situation where you have a multi-axial stress state applied around the crack, you can just take the stress contributions from each of the various modes. So how do we define these stress expressions? Well, this depends on the various modes. So the singular stress fields, and these stresses are in Cartesian coordinates. So what we have is we can define detailed expressions for the stress in the x direction, the stress in the y direction, the in-plane shear, and because this is plane stress, for the out-of-plane stress, it's 0 for plane stress, or the sum of the stresses multiplied by the Poisson ratio for plane strain. And of course, our transverse shear stresses are 0. And so we have for mode 1, the stress in the x direction is this expression here. Here's our k over the square root of 2 pi times the radius, and this is our function, of the angle theta. And we have similar expressions for the y stress and the shear stress. And for mode 2, we have the various expressions for the stress due to mode 2 loading, and all of these still have that stress intensity factor over the square root of 2 pi times the radius, but these angles, the functions of the angle are different. The functions of the angle are different depending on the loading. And we have expressions for the stresses. We also have expressions for the displacements in the regions around the crack. And here, because it's a displacement, now we have to throw in some we have the radius in the numerator instead of the denominator, but also because it's a displacement and not stresses, now we have to start throwing in some material properties. So we have the shear modulus, and we have this parameter kappa, which is a function of the Poisson's ratio, and the value of this function kappa is different depending on if it's a plane strain or a plane stress problem. So these are generalized stress functions for the stress fields ahead of a crack tip. All we're specifying at this point is that it's a linear elastic isotropic material. And then finally, for mode 3, the out-of-plane shear, here we don't have any normal or shear stresses in plane. All we have is our transverse shear stresses and our out-of-plane displacements. Once again, the stresses are just function of the radius, and our function theta, our mode 3 stress intensity factor. And for the out-of-plane displacement, we have the shear modulus term running around in there. So now we can look at a couple of special cases. Let's look at the mode 1 right along the crack tip. So we're saying right along the path of the crack, where theta is equal to 0, right along the path of the crack. So in that case, if we look at our expression, sine of theta is 0, so it makes these terms go away. So all we have is the 1, and cosine of 0 is 1. And similarly, if we look at the normal stress in the y direction, once again, if theta is 0, the sine of theta is 0. It makes our sine terms go away. and our cosine of theta is 1, so that sets it here. So what we have for the special case of so when theta equals 0, we have the special case that our stress in the x direction is equal to our stress in the y direction, and it's just equal to the mode 1 stress intensity factor divided by 2 times pi times the radius. And for the shear stress, if we look here, we have sine of 0 is 0. So, and these are all just multiplicative. There's no one term in here. So when theta is equal to 0, these two terms are 0, which means this whole term is 0. So right around the plane of the crack, we have that our shear stress is equal to 0. So if we go back to our original here, so right along the plane of the crack, if we go back to our little element with the various stresses applied, the x direction and y direction stresses are equal to each other, and the shear stress here is 0. So what that also means is, remember when we talked about our review of elasticity theory, that we talked about principal stresses is the case where we just have normal stresses, and our shear stresses are equal to 0. So what this means is the crack plane, so under pure mode 1 loading, the crack plane is a principal plane. We only have normal stresses. We don't have shear stresses. Now what we talked about a little bit ago is that all these things we're doing with our stresses, they're only true right around the crack tip. Because if you look, the fundamentals, the stress intensity factor divided by 2 times pi times the radius, well, when the radius gets big, this term here gets close to 0. So this term here gets close to 0. So it doesn't contribute things anymore. So because this is the idea, you have way out in some infinite distance, you have, some applied stress. So once you get far enough from your crack tip, then the only stress that's relevant to the structure is just your far field stress. So the stresses far from the crack tip are governed by the remote boundary condition. So if we have a uniform tensile stress applied horizontally in terms of this discussion, the stress approaches are constant value. So this singularity dominated zone is the point where if we plot our stress as a function of radius, first of all, notice as we get close to r equals 0, we start hitting an asymptotic value because the stress is infinite right at r equals to 0. But also, it's only in this singularity dominated zone where these stresses are relevant, because this is the area where the radius is small enough that this term starts getting big enough that it starts contributing to the stress, and so when you start so far enough from the radius, if you think that your total stress is equal to your stress at infinity plus your stress due to the crack, where this term here represents your stress due to the crack. It's only when you get sufficiently close to the tip of the crack where this term starts getting big enough. You see a little bit, it starts growing a little bit, but it's only where you start getting the zone really near the crack where this term starts to dominate, and it provides a significant contribution to your stresses. So the stress so the other thing to note here is the stress and and so we define the singularity dominated zone, and again, it's defined nebulously. It's just where we have these tables here. It's just that these various stresses that we compute using these tables here grow large enough that they provide stress levels significantly greater than our far-field stress. And so the stress and the level and the stress intensity factor, which is a material property, the higher the stress intensity factor, and this is a material property, the higher the stress intensity factor, the farther away from your crack tip does the crack affect the response of the material, and it also controls the magnitude for which the stresses increase as you get closer to the crack tip. So as you see here, the higher stress intensity factor, the more the stresses around the crack are affected by the region right near the crack. And the stress intensity factor completely defines the crack so the stress intensity factor completely defines the crack tip conditions. So if you know the stress intensity factor, you can solve all of the components of the stress and strain and displacement as a function of the radius and the angle. And the idea that you can use just one single parameter, the stress intensity factor, to completely define the stress state around the crack tip turns out to be one of the more significant and important concepts in fracture mechanics. Okay. So in order for the stress intensity factor to be useful, you need to be able to determine the stress intensity factor from remote loads in the geometry. So closed form solutions for the stress intensity factor, and we're going to go over several of them, have been derived for a number of simple configurations. Now, for more complex situations, because we're going to do just some very simple configurations. So what you can do is for more complex situations, the stress intensity one way you can estimate the stress intensity factor by experiment or numerical analysis. And also we're going to talk about a little bit is that if you know the stress intensity factor for a couple simple cases, if you can take your more complex case and consider it to be a combination of several simpler cases, you can use that idea to estimate your stress intensity factor. So one configuration for which a closed form solution exists is our old friend, the through crack in an infinite plate subject to a remote tensile stress. We've done this before. Remember, the crack has a crack length 2A. We have B, which is our plate thickness, and we have our remote tensile stress sigma tensile stress sigma apply to the plate. So since this remote stress is perpendicular to the crack plane, if we go back to the idea of how we define our modes, Since similar here in mode 1, the load is perpendicular to the crack plane. So since that's the condition for our case here, that this loading is pure mode 1 loading. And linear elastic bodies undergo proportional stressing. That is, all the stress location components in all locations increase in proportionally to the remotely applied forces. So if you apply as you increase your loading remotely, the stresses all increase by the same proportions, by the strain ratios. So the crack tip stresses are proportional to the remote stress, and the stress intensity factor is proportional to the applied stress. And if we look at how these equations were set up, and if we look at how the equations are set up, the stress intensity has units of stress times the stress times the square root of length. So to write that, yeah. So yeah. So since the only relevant length scale, and when we talk about here, the only relevant length scale is our crack size. So we can say that our stress intensity factor has the form that our stress intensity factor is equal to some function of the stress multiplied by the square root of the half crack length, because the only length dimension of significance here is the crack length, because we're looking at an infinite plate. So it goes off in infinite directions, vertically and horizontally. So the only length we have to deal with is the crack length, and we always just deal with the half crack length A. And the actual solution for this case, which in one of the appendices in the back of the book, they go through in lots of details, it can be, using that wonderful expression, it can be found that for the infinite plate subject to mode 1 type of loading, that the mode 1 stress intensity factor is equal to the stress times the square root of pi times the half crack length. And it's a fairly complicated derivation, but you do end up with this simple expression. So the amplitude of the crack tip singularity, the amplitude of the amount that the stresses are multiplied by the crack tip, is proportional to your applied stress and the square root of the crack size, because pi is just a scalar number. And for mode 2, all you do is you take this normal stress and replace it by the shear stress, and you get a similar expression. So the mode 2 stress intensity factor is also just proportional to the applied shear stress and half of the crack length. Okay. So the amplitude of the crack tip singularity for this configuration is, proportional to the remote stress and the square root of the crack size. We just talked about that. Now, a similar simple case is for a semi-infinite plate. So it's still infinite vertically, but now we have a defined edge, and it's still infinite going off to the right, but we now have a defined edge on the left. And so we have a defined edge on the left, so it's a So it's an edge crack. So, and the way we can get this is if we take this and we just slice it down the middle, we'll get learn this time. Okay. So we just take this and slice it down the middle, and we get this configuration. And the stress intensity factor for this situation is as follows. So we have that the mode 1 stress intensity factor is equal to 1.12 times stress times the square root of pi times the half crack length. And you can derive this also. It's beyond the scope of our discussions, but this 12% increase, so you see it's 1.12 and not 1, and the reason for this increase is because you have different boundary conditions at the free edge, because when you have the free edge, you have edge effects, which it does serve to focus your stresses. And the way to look at it is if you look at this figure here, the free edge, because of the interplay of the boundary conditions and your edge effects, you see it opens up the crack just a little bit more. You see this dotted line is the through crack. This dotted line is the through crack. And for the case of the edge crack, it's less constrained, and it just opens up a little more. So while the through crack forms a purely elliptical shape because we're not constraining this edge here, it allows it to open up just a little bit more. So that's why we get that 1.12. And it seems like it's a number just pulled out of thin air, but there is a rationale behind this number. So another case we're going to look at is we're going to consider the through crack in the infinite plate, where the normal to the crack plane is oriented at some angle beta to the stress axis. There's no reason why that can't happen. Now, in this case, if beta is not equal to 0, the crack experiences both mode 1 and mode 2 loading, because if you look, we talked about these ideas of when we talked about principal stresses, we talked about this idea of stress transformations a little bit, that as far as the crack's concerned, if we transform, and always when you talk about stress transformations, the important point to remember is that the actual stress state is the same. All we're doing is we're changing our reference system. So we have a system in terms of the crack where we have an x prime axis along the crack and a y prime axis perpendicular to the crack. And what happens here, so even though in our what we call our structural or global system, we're still only applying this unidirectional stress in the vertical direction, but as far as the crack is concerned, along this new coordinate system related to the crack, it's seeing normal stresses along the plane of the crack, normal stresses perpendicular to the crack, and it's also seeing shear stresses. Now, the normal stresses don't contribute to the opening of the crack, but these normal stresses perpendicular, that's mode 2. But we also have this mode 1, I'm sorry, but these shear stresses here, as far as the crack is concerned, means that it's also mode 2. So because we rotated the crack, as far as the crack's concerned, it is seeing stresses, it's seeing both normal and shear stresses in the in the plane of the crack. Now, because as long as everything's still in plane, the mode 3 stress, there is still no mode 3 loading, because as long as we just rotate in plane, everything is just within the plane. It's only if we rotated the crack out of plane, then all of a sudden we'd start having mode 3 in there too, because as far as the crack was concerned, it would be in a new coordinate system. It would be seen out of, as far as it's concerned, it'd be seen out of plane stresses. But the point I always emphasize, because students always have trouble in this is still, this stress state is the exact same as this, the loads and displacements the body sees are the same. The only thing is the stress has changed, because stress is a mathematical invention. Load and displacement are real physical quantities. Stress and strain are mathematical conventions, and our stresses and strains change based on the coordinate system that we're looking at. So we talked about this. Normal stress creates mode 1 loading. The shear stress creates mode 2 loading. And we just talked about that. So the stress intensity factors for the plate can be, we'll relate the stresses in this rotated system to our globally applied stress. So, for example, our mode 1 stress intensity factor is our normal stress in the 1, 1 direction times the square root of pi a. But if you learned about principal stresses we talked about, it also relates to the ideas of Morse circle that you learned about in sophomore strength of materials. If you take continuum mechanics, you'll go into a lot more detail about stress transformations. But with all that being said, we can also say that this is equivalent to our applied stress times cosine squared of our angle of rotation beta times the square root of pi a. And that's just because, we're not going to talk about it. You can say that this stress is just equal to sigma times cosine squared beta, not beta. And similarly, we can say that our mode 2 stress intensity factor is equal to our shear stress in our rotated coordinate system multiplied by the square root of pi a. But with our stress transformation, we can say that this stress is equivalent to our applied stress times sine of beta times the cosine of beta times the square root of pi a. So we don't need to explicitly compute the stresses in our rotated system, even though we can with our stress transformation equations. Just by knowing the angle of rotation and the far field stress, we can compute what our mode 1 and mode 2 stress intensity our mode 1 and mode 2 stress intensity factors are for the case of a rotated crack. And a couple other things to note here. When beta equals to 0, cosine of 0 is 1, sine of beta is 0. So the mode 1 just is sigma the square root of pi a. Sine of 0 is 0. It gets rid of all of this mode 2. So the mode 2 stress intensity factor is 0 right along if beta is equal to 0, and that makes sense. Plus, you might have learned about in some of your classes, but just say at 45 degrees, when beta is equal to when beta is equal to 45 degrees, you can find, it's beyond the scope of this class, but you can find that the shear stress is a maximum at an angle of 45 degrees. So if the shear stress is a maximum where beta equals 45 degrees, it goes to say that the mode 2 stress intensity factor is a maximum at beta equals 45 degrees. And so this is just an introduction to this. We're going to later go into more detail on what happens under fracture, under mixed mode conditions. And the last point we'll talk about before we take our break is another simple configuration is a penny-shaped crack in an infinite medium. So here we have a bit more of a radius. I mean, it's a penny through the shape of the crack. It just looks elliptical because of the plane. So imagine a circular penny-shaped crack in the middle of your structure with the radius of the penny equals to A, and the radius of your circle equals to A. And for that case, our mode 1 stress so in this case, our mode 1 stress intensity factor is equal to 2 divided by pi times sigma times the square root of pi times A. So this equation has the same form as the previous relationships for through crack, except the difference is that instead of the crack length being our what we call the characteristic length, now it's the radius of our penny-shaped crack, which is the basis of our length. So with that, I think it's a good time to take our break. So we'll take our break now and we'll come back at 20 after 6. Okay. So we talked about the simple case of a through crack and a penny crack. Now we'll talk about the more general case of an elliptical or semi-elliptical crack. So the penny shape was basically circular. We have an elliptical or a semi-elliptical, and the idea of the semi-elliptical is that right up to the edge is the major dimension. So, a couple important things to note. First of all, there's two length dimensions needed to characterize the crack. We have a length 2c, and we have this dimension, 2a that goes into the plane. And here for the semi-elliptical, it's still 2c, and it's just the half dimension a. So what we have is the basic format for the stress intensity factor is the same, but notice there's a couple of different things. First, for the elliptical, we have this parameter q. And what this parameter q is, and the way to look at it, so this elliptical, it's an embedded crack. So it's a crack just set in the middle of our structure. And then the semi-elliptical is a surface crack where it goes up to the edge, as I said. So anyway, the format of the stress intensity factor is basically the same, but we have this flaw-shaped parameter q, and this flaw-shaped parameter q, and we have this expression here, and this flaw-shaped parameter is the same for both the fully elliptical and the semi-elliptical, and it's obtained using the idea of elliptic integrals. And again, in the appendix in the book, I think it goes through the gory detail of how to come about this. And also, we have our f of phi, which our f of phi, which is a function of the angle as we go along the crack. So phi goes from 0 to 360 as we go along the dimension of the crack. And then for the semi-elliptical, we have this lambda term, which is a surface correction factor. And the surface correction factor is just an approximation, but it's just account for boundary conditions and everything that's involved with the fact that your crack goes all. So unlike the fully elliptical, where it's just sitting right in the middle of our embedded body, to account for the fact that for the half elliptical, it's right up against the outer surface of our block, we have this approximate correction factor to account for the shape. And the phi, the angle, is defined by this little figure here. So phi starts at 0, goes around to 90 for the penny-shaped crack. The crack is a nice circle. You see, for the fully elliptical crack, it's not a circle, but still, we can still use phi to define the angle. And obviously, for the fully elliptical, phi can go from 0 all the way around to 360, where for our surface crack, phi only goes from 0 to 180, and we have this f of phi term here, which determines what our stress intensity factor is at each point along the radius of the crack. And instead of the radius like we have for we have this geometry term A, which controls the stress intensity factor as a function of the geometry of our crack. So when A is much less than C, The stress intensity factor varies along the crack front. So when A is much less than Z, it's less than C. It's almost just a through crack. So the stress intensity factor just varies along the crack front, and the maximum stress intensity factor is at phi is equal to phi is equal to 90 degrees, because we have that cosine squared of phi running around in here. And this expression for Q is just an approximate solution for Q, and the surface correction factor is also an approximation. So what we have, we've now gone through for a through thickness crack, for penny-shaped crack, and for elliptical cracks. We've defined some specific expressions to compute the stress intensity factor. Now and we talked about all this. Now the next thing we look at, everything we've talked about for the most part is in infinite plates. Just getting back here, the idea, we see that the plates go off into infinity, horizontal and vertically. And we did talk about the one case of an edge crack where we did specify one of the edges. And this is fine with the dimensions of the crack are very small with respect to the dimensions of your structure. But there's also so most of our configurations consist of a crack with a simple shape, so either rectangular crack or an elliptical crack in an infinite plate. So as I talked about, the crack dimensions are small with respect to the size of the plate, and our crack tip conditions aren't influenced by the external boundaries. Now, in a lot of real structures, first of all, as your crack size grows, it could be getting closer to the edges of your structure, or if you're looking for a crack in a smaller plate, all of a sudden your outer boundaries can begin to exert an influence on the crack tip. Now, the problem with this case is, in these cases, a closed form stress intensity solution is usually not possible. So let's look at a cracked plate subject to a remote tensile stress. And this figure schematically illustrates the effect of the finite width on the crack tip stress distribution. So what we have here is we have our lines of force, which represents the stress and how the stress is affected by the presence of the crack. Now, the local stress, so our stresses anywhere in the structure are proportional to the spacing between the lines of force. So far away from the crack, you can see that the lines of force are equally spaced, so we have no stress contributions. Now, the big thing that contributes is the fact that stress can't be transmitted through a crack. Makes sense. The crack is empty space out there, so you can't transmit stress through an empty crack. So these lines of force are diverted around the crack, resulting in local stress concentrations. And you can see here, even in the infinite case, right around the tips of the crack, we have a concentration of these lines of force indicating we have stress concentrations. It makes sense based on everything we've talked about before. And in this infinite plate, the lines of force at some distance W from the crack, which is where we have our influence, because the lines of force are bent, that means we have local forces in the x and y directions, because even though far field is just unidirectional, because these lines of force are bent due to the presence of the crack, locally we have, our because if you think that our stress is along our lines of force, well, here, because it's bent, to fall along the lines of force, it's kind of going this way. So because it's no longer aligned vertically, it has component, even though locally it's still along the line of force, but when you look at our global coordinate system, you have force components in the x and y direction. But when you look at a finite width plate, you have a problem. By our boundary conditions along this width, this force in the x direction has to be equal to 0, because you can't have forces or stresses along a free edge. So what happens then is because these right along this edge, our line of force has to be vertical. So you see, when we're getting, unlike in the infinite plate where their lines of force are really bent at this distance 2w, if we specify that the width is only 2w, right near here, right near the edge, the lines of force aren't really bent, they're almost straight, because they have to be perfectly straight at the edge. So therefore, to meet all these conditions, the lines of force have to be compressed. You'll notice that even a little bit around here, the distances between the lines of force are less. So that means when you have a finite width plate, you have a higher stress concentration than you do in the case of a infinite plate, which means you have a higher stress intensification at the crack tip. So, yeah, talked about all that. So one way to approximate this finite width boundary condition is you can represent the same thing, where if you still look at our infinite plate, but you look at not just one crack in the infinite plate, you have a series of collinear cracks in the infinite plate. So this way, when these cracks interact with each other, you'll still have kind of the same effect as you do with the finite width plate. And therefore, and what you can do then, you can solve and you can derive, and you can get that for this case of the collinear cracks, that our mode 1 stress intensity factor is still square root sigma times the square root of pi a, but now we have this correction factor of 2w divided by pi a times the tangent of pi a divided by 2w, all to the 1/2 power. So this is our correction for this case of collinear cracks. Now the thing you can look here is that as this A over W ratio goes to 0, the tangent of 0 is 0. So as A over W goes to 0, this becomes 0. So even though W over A still starts going to infinity, if this is going to 0, 0 times anything is still 0. So you end up with the infinite plate solution of just sigma the square root of pi a as A over W goes to 0. And conversely, as A over W goes to 1, so basically you get to the point where the crack is right up against the edge of the plate, or in this case where we have the cracks practically touching each other, then the tangent then A over W goes to 1, the tangent of 90 degrees is infinity, so that leads to our singularity. So that means that our mode 1 stress intensity factor is asymptotic to the case where A over W equals 1. Okay? Now, more accurate solutions for through crack in a finite plate have been obtained from finite element analysis, and solutions of this type are fit to polynomial expressions. And just one example that's been obtained in the literature is sigma, the square root of pi a times the secant of pi a over 2w to the 1/2 1/2 power time multiplied by a term 1 minus 0.025 a over w squared plus 0.06 a over w to the 4th. Now, you can see this looks like a fairly complicated expression, but an interesting thing is that if you actually plot that in this plot, the open circles here, are by that original, and we're plotting the K1 divided by sigma to the square root of pi a times the A over W ratio. So the open circles are this expression here, the tangent expression. The open squares are this full expression here. And then the closed circles, where if you just look at this secant term and you ignore all this stuff. So when you look at that, a couple of points is that for up to about A over W equals A over W less than 0.6, the simple analytical solution with the tangent is pretty darn close to the finite element solution. It's within 7%. And all the way up to A over W equal, and it's not that far even, not that different even among the rest of things. And also the if you compare the line with the circles and the line with the squares, unless you really, really look carefully, you can see that they almost lie on top of each other. It's just right at this final point here where you can see a little bit of a separation between the two. But the secant correction is very close to the finite element solution. The area is less than 2%. So the polynomial term in this finite element based equation contributes very little. And if you're just doing hand calculations, you can neglect it. So basically, you can either use the tangent. For all practical purposes, you can either use the tangent equation or this equation here and just the secant part of it and get reasonable approximations for your finite widths mode 1 stress intensity factor. Okay. So we have for several different configurations, and always when we look at here, the thing to keep in mind is that and it's listed in just a little tiny footnote at the end, but just to emphasize, we have that for all of these, our stress intensity factor is equal to the load divided by the thickness B times the square root of this W dimension, where the W dimension is, and for the W dimension, these are all for finite width specimens. So this W dimension is defined in these various and sundry configurations times our function of A over W. And that's what's listed here for these various things. There's various expressions for this function of A over W, where A and W are dimensions defined here. And so we have, for very simple case, single edge notch tension for a finite plate, and this is where it's in tension. And the single edge notched bend, and just to give you a hint, is that in your homework where it refers to a 3-point bend specimen, just to avoid any issues, this is the configuration looked at for the 3-point bend represented in the homework. I figured I copied the text from the problem as given somewhere, but I'm also thinking that I don't want you to get screwed up by something by misinterpreting that. That be in my mind a not relevant thing to get messed up on. But anyway, so this is our function of A over W for the case of the single edge notch bend or a 3-point bend. Or we have a plate with a crack sitting in the middle, or we have a plate with a crack on each edge, and these are all for finite width specimens. And finally we have for a compact tension or compact compression specimen. And for all of these, the things you have to look at this geometries, because particularly for the most part, the dimensions are fairly consistent. But note, for example, center crack tension, it's 2A, not A, if you're given a crack length. And for this compact tension or compact tension specimen, everything's along the horizontal direction. So you just have to, when you're using these handbook type of things, just be sure to match up your load type and be sure to note very carefully what the different dimensions represent. And likewise, the same way in this 3-point bend on the top, because it's split in two, it's P divided by 2, it's P here. So just little things to pay attention to when you're solving a problem. And also another thing, just for interest, is that you can plot these stress intensity solutions for the various configurations. And the thing to note is that everything else being equal, the single notch bend specimen is going to have the highest stress intensity factor, and the compact specimen will have the lowest. So the type of specimen you have can significantly affect your stress intensity factor, and thus your stress magnifications around your crack, and which also leads to how easily or not easily it fractures. Okay. So although stress intensity solutions are given in a variety of forms, they're always ultimately, and this is something where I actually forgot to put the equation in the notes, but I'll write it out here. It's always equal to, the stress is equal to some so I can just write it down quickly before class. Oops, I did. Yeah, did mess it around. Okay. So we have our So our stress intensity factor for, modes 1, 2, or 3 is equal to sigma times the square root of pi a times some correction factor. So sigma is our applied stress. A is the characteristic crack dimension, whether it's the half of the crack length, the radius of the crack, the major radius of the ellipse. It's some characteristic length of our crack. And then all these various things here, this not dimensionless contact this is our function of A over W, which is dependent on the geometry and the mode of loading. So everything's basically the same. It's just depending on the type of specimen you have. You can have these complex expressions which are related to the crack geometry and the specimen geometry. Okay. So, sample problem. So we're actually going to show for our single edge notch tensile panel. So for this case, we're actually going to demonstrate that when A is much less than W, so for the case where the plate is really, really wide in terms of the crack, that we end up with our mode 1 stress intensity factor is equal to 1.12 times the stress times the square root of pi a. So we're going to show that for the case where A is much less than W, that this whole complicated expression reduces to a very simple number. So what we do is, as we talked about, for all of these expressions, it's equal to load times the thickness divided by the thickness times the square root of the width times our function of A over W. And what we can do now is we can play a little bit of a math game. Is what we're going to do is we're going to say that we're going to take this P over B times the square root of W times our function of A over W. And what we're going to do is, have this. We're going to say that it's equal to P over B times W times our function of A over W times the square root of W over pi times A times the square root of pi A. Now this is all math games, but if you look, the square root of W divided by W is the square root of W. Multiplying and dividing by the square root of pi A. But the important thing also we can look at is by doing this, B times W. So the thickness times the width is equal to the area. So here we are. Yeah. So B times W is equal to the area, and thus the force over the area is equal to our stress. So we can say that this P over B times the square root of W times our function of A over W is just equal to some parameter gamma times sigma times the square root of pi times a, and gamma is equal to our function of a over w times the square root of w divided by pi a. So now, because a is much less than w, we can look at our we can look at our equation, we can look at our expression here, and we can start seeing what happens when a over w gets small. Well, when a over w gets small, this starts getting close to zero, this starts getting close to zero. Even though they're both getting close to zero, they're both getting close to zero, so they basically become one, so anything divided by itself gets to one. This a over w term starts getting to zero. This a over w term starts getting to zero. Sine of zero is zero, so all you have left is 1 in here. So so in the limit of a small flaw, that our limit as a over w goes to zero of our function of a over w is just equal, well, our limit as a over w goes to zero, we get the square root of pi a over w times 0.752 plus 0.37. And therefore, our limit as a over w goes to zero of this gamma term going back here. Oops. Yeah, so we had, oh, so yeah, so we had this, yeah, this, so our gamma term was the function of a over w, the square root of pi a. So yeah, so this is basically, yeah, so this is our limit of gamma. So our limit of gamma as a over w goes to zero, and this is, yeah, is equal to 1.122, because we had the square root of w over pi a, and so we take the pi a over w to get rid of this, and we just looked at this expression up here, and we saw that all we had left was the 0.752 and the 0.37. Okay, so I think the last big thing we're going to go into a little bit of detail today is the principle of superposition. So for linear elastic materials, individual components of stress, strain, and displacement are additive. So if you have normal stresses imposed by different forces, you can add them to obtain the total normal stress in the x direction, but a normal stress can't be summed with the shear stress. So similarly, stress intensity factors are additive as long as the mode of loading is consistent. So we can say that our total stress intensity factor is equal to the mode 1 stress intensity factor from loading A plus our mode 1 stress intensity factor from loading B plus our mode 1 stress intensity factor from loading C. But what we cannot say is that our total stress intensity factor does not equal to the stress intensity factor from mode 1 plus the stress intensity factor from mode 2 plus the stress intensity factor from mode 3. So in many instances, the principle of superposition allows stress intensity solutions for complex configurations to be built from simple cases. We've had all these tables and charts we've shown where we've done the stress intensity factors for simple cases. Real life isn't always a simple case, but the idea of the stress intensity factor is it allows us to look at some of these more complicated situations and build it up into simple problems that we know how to do. So for example, consider we have an edge-cracked panel subject to both combined axial loading and three-point loading. Now, we had equations for the case of an edge-cracked panel. We have a subject to tensile loading. So if we go back here, come on. Yeah, we have an edge cracked panel subject to tensile loading. We have an edge cracked panel subject to 3-point bending loading. So what we can do is we can say that our total, here's where I want it. So we can say that our K1 total is equal to our K1 for the membrane loading plus the K1 for the bending loading. And so it's equal to 1 over E times the square root of W times our membrane load times our function of A over W for the case of the edge cracked under tensile loading plus the membrane load, the 3-point bending load, times our function of A over W for the case of 3-point bending. And we take these, add it together, divided by the thickness and the square root of our W term, and we have our solved problem. Okay. So what we have is we have a semi-elliptical surface crack subject to an internal pressure. So this is not something we've talked about. We've talked about a semi-elliptical crack subject to a far field loading, but not a semi-elliptical crack subject to just loading right along the cracked edge. So what we do is we apply the principle of superposition. We know the solution for a semi-elliptical crack subject to remote tension. We did that. But what we can do to get the equivalent point is that we can say that this far field loading can be transferred down, and if we take this condition and we impose a uniform compressive crack on the edge of the crack, the stress intensity factor goes to 0 because the crack face is closed and the plate behaves as if the crack wasn't present. So what we do is we subtract this from this. And we can say that, so we can say that our K1 for our condition A is equal to K1 from our condition B minus K1 from position C. And because it's subtracting, what we do here is because we're subtracting this from this, these P's cancel out, and these P's cancel out, and this negative p, we subtract a negative, and it becomes a positive, and it becomes a positive load on the edge of the crack. And this is equivalent because we have the positive p going in here and the negative p going in here. So we're really not so it's effectively a zero loading condition. So what we say is then that this is equal to our edge correction factor times our load times the square root of pi a over q times our function of the angle minus 0, which is just equal to times our p times the square root of pi a divided by q, our function of phi. So this is just a simple illustration of a more general concept. Stresses acting on the boundary can be replaced with tractions that act on the crack face such that the two loading conditions result in the same stress intensity factor. So we have an uncracked body subject to boundary tractions as shown here, and this boundary traction results in a normal stress distribution on this plane here. And to confine the problem to mode 1, let's assume that there's no shear stresses present. So this assumption is made for the sake of simplicity. The basic principle can be applied to all three modes of loading. So what we're saying is that this load here, where we just have loading on the outer surface, we can take this condition here and add it to this condition here, and we result in the same thing. Because if we add this, we have positive stresses on the crack and negative stresses on the crack. So these two cancel out. But however, when we look in terms of stress intensity factors, we can say that our stress intensity factor for A is equal to the stress intensity factor for condition B plus the stress intensity factor for condition C. But since we have positive and negative loads here, this is equal to 0. So we just have the stress intensity factor for B, which says that if we have loads along the crack face, it's the same as if we had the loads along the outer edge. And thinking about it, I actually like this example better than the sample problem we just did, because I think a minute ago, because this explains it better. But it's all the idea that this is a case where we were able to take the load on the crack face and we were able to transfer it to something we know. And just in general, the idea is that we can take conditions that are different from how we encountered and work to transform them into combinations of conditions that we have specified handbook solutions for. So with that, do we have any questions? Okay. If not, we'll call it a day for today. Have a good week, and I'll see you next class.